Hello. As a part of the series of video lectures that explain the instruction set of the ARM processor, this current lecture explains in details the branching instructions and some special instructions of the ARM processor. Branching instructions. These instructions are used to make a branch in a program. That means to transfer the execution from one point of the program to other, or to call a subroutine. Let's discuss the instructions one by one. Branch condition followed by label. Here B is for branch. So this instruction transfers the execution to the specified address which is given in terms of this label when this condition is true. So in other words, this is a conditional branching instruction. Label is actually a 24-bit relative address. Actually it's a 24-bit signed number. It is added to the current value of the program counter to obtain the branching address. Because it's a 24-bit signed number, its range is like this. Out of 24 bits, 1 bit is sign bit, and therefore plus minus 2 raised to 23, which is plus minus 8 mega, is the range of this number, and therefore this allows the branching over maximum range of plus minus 8 mega instructions. So this label indicates how many instructions ahead or how many instructions backward the branching is to be made. So that's how this specifies the number of instructions after which or by which the branching is to be made. Because every instruction is 32-bit wide, it occupies 4 locations in the memory, and therefore plus minus 8 mega instructions multiplied by 4 bytes per instruction or 4 locations per instruction, and therefore totally it can branch over plus minus 32 megabytes in the memory. So maximum range of making a jump is plus minus 32 megabytes in the memory. So that's how this instruction works. The address which is given is a relative address, and it's a conditional branching instruction. As an example, consider this instruction BCC label. CC is the condition carry clear. So this instruction is branch if carry is clear to the given address. So this instruction will jump to the address when the carry is 0. Now these instructions are for implementing subroutines or calling subroutines. The instruction is branch with link. Once again, it's a conditional instruction and the address is given in the form of label. So branch with link, condition and label. Okay, so this is used to call a subroutine. When this instruction is executed, the current value of the program counter is stored in the link register. As we know that when this instruction is being decoded and executed, the program counter will hold the address of the next instruction. That will be saved in the link register R14, and then whatever address is generated by using this label, that address will be loaded into the program counter, and therefore the execution will be transferred to this new address. So that's how this calls a subroutine at the given address. At the end of the subroutine, the execution may be transferred back to the main program simply by copying the content of the link register R14 back to the program counter R15. because this register holds the back address, and that can be simply copied into the program counter, say by using a move type of instruction, and that will effectively take the execution back to the main program. So that's how this instruction works. It's a branch with link instruction, conditional instruction, and uses relative address. Other instruction is branch with link and exchange followed by label. So this is again an instruction which calls a subroutine. It's an unconditional instruction. There is no condition field here, and this instruction also changes the mode of operation of the processor from ARM to thumb mode. That's why it is called as branch and link with exchange. It changes the mode of operation from ARM to thumb. So actually, when this instruction is executed, or it is being executed, the steps taken by the processor are like this. It will load the current content of the program counter into the link register. It will set the thumb flag in CPSR register. Okay, so the state of operation is changed from ARM to thumb, and then it loads this new address into the program counter. Therefore, it calls a subroutine. So that means when this instruction is executed, this is an ARM instruction. It is a part of the ARM program. When this instruction is executed, it will call a thumb subroutine. It will call a subroutine, and at the same time it will change the mode of operation of the processor to the thumb mode, and therefore that subroutine should be in terms of thumb instructions. So that's how this instruction calls a thumb subroutine. So this is for calling an ARM subroutine from the ARM program. This is for calling a thumb subroutine from the ARM program. Okay, one more instruction under branching type is branch with exchange followed by condition and a register, say RM. This instruction is again a branch instruction. It transfers the execution to the specified address when this condition is true. Now here the address is an absolute address given in a register of the register bank. It's a 32-bit register, so it will hold the 32-bit branch address. And also when this instruction is executed, the mode of the operation will be changed. So it is branch with exchange. So when this instruction is executed, if the condition is true, then these steps are taken. The instruction will load the content of RM into the program counter, so the branching will occur, and then depending upon the bit D0 of the register RM, the mode will be changed to ARM or thumb. It will remain in the ARM mode or it will go to the thumb mode depending upon bit D0 of the register RM. Typically when bit D0 of the register RM is 0, then the thumb bit is reset to 0, and therefore the processor remains in the ARM mode, okay, after the branching. And if that bit is 1, then the thumb bit is set to 1, and therefore the mode is changed to thumb mode, and therefore after the branching, the instructions which the processor will execute, or it is supposed to execute, should be thumb instructions. And therefore this is a branching instruction, conditional branching instruction, and it branches to a location in the memory where either there is a thumb instructions or there will be ARM instructions or there will be thumb instructions. Okay, so it's a conditional branching with exchange. It uses absolute addressing mode. It gives absolute address in RM, branching address, and after branching the processor may remain in the ARM mode or it may go to the thumb mode. Okay, so these are the different kinds of branching instructions: conditional branching with relative addressing, branch with link for calling subroutines, either plain branching with link or branch and link with exchange. So this is used to call a thumb subroutine, or simply branch with exchange. It may go to the instructions which may be either ARM instructions or thumb instructions depending upon the bit D0 of this RM. Now let us discuss some special instructions. Instruction SWI followed by 24-bit immediate number. It's a software interrupt instruction. It is actually used to call a supervisor routine. There are some monitor routines which are the part of the operating system, which are used to handle the different hardware modules of this computer system, ARM based computer, and those routines can be executed only in the supervisor mode. Normally the user programs are operated in the user mode. User mode is non-privileged mode, and therefore if the program in the user mode wants to access any hardware module of the system, then it has to go to the supervisor mode and then execute the corresponding program or corresponding routine to handle that hardware module. So this instruction allows the user to access the hardware modules by executing different routines in the supervisor mode. That's why it is called as supervisor call. This is also called as a supervisor call. When this instruction is executed, supervisor mode is entered by the ARM processor. The ARM enters into the supervisor mode from user mode, and for that it follows this sequence of operations. It's a ARM exception entry sequence. So whenever any exception occurs, it may be occurring of an interrupt, it may be detecting some undefined instruction, any kind of exception occurs, then the ARM follows these steps to enter the exception mode. Okay, so same sequence is followed when this instruction is executed. That means when this instruction is executed, the ARM processor will first of all save the address of the next instruction in the link register of the supervisor mode. R14 is a link register, and this is R14 underscore SVC in the supervisor mode. Then it will save the content of CPSR, current program status register, into the SPSR of the supervisor mode. Then it modifies the control field of CPSR. Particularly, it manipulates or it modifies the control bits so that the supervisor mode is entered. That means the bits 0 to 4 of CPSR should be like this for supervisor mode, and therefore it modifies these bits to this pattern so that the supervisor mode is entered, and also it disables the IRQ, interrupt request, and for that it has to set bit number 7 of CPSR, and therefore these bits which are the part of the control field of the CPSR, they are modified as shown here, and then the program counter is loaded by the vector address associated with this software interrupt instruction. Okay, and therefore obviously the execution is transferred to this new address. Okay, so that's how when this instruction is executed, the address of the next instruction is saved in link register of supervisor mode. Then CPSR is copied into the SPSR of supervisor mode. Appropriate bits are modified to change the mode and disable the IRQ, and the execution is transferred to the vector address corresponding to this SWI instruction, which is as shown here, and execution is transferred there. Okay, now the question is, what is the use of this 24-bit immediate number? Actually, this number is used to indicate the function number. When this instruction is executed, the processor enters into the supervisor mode, and then this 24-bit number tells the processor which of the various monitor routines is to be executed. So this function number, according to this function number, the processor will execute one of the monitor routines as per the requirement, the routines which actually are used to handle the different hardware modules. So it is similar to your INT21 instruction of processor 8086. When that instruction is to be given, the function number is stored in register AH. So that therefore when that interrupt occurs, then depending upon the function number, the processor executes the corresponding monitor program. So in the similar manner, here this 24-bit immediate number indicates the function number. Exactly how it is used when the execution is transferred here, let's discuss that. Use of that 24-bit immediate number. Actually, this number is used to implement what is called as software interrupt handler. Okay, so this is what happens when that instruction is executed. SWI, software interrupt instruction, is executed. So execution is transferred to this address. At this address, there is a branch instruction which transfers the execution to this software interrupt handler, and that handler is basically contains this kind of instructions. Here actually that SWI instruction, software interrupt instruction, is read into a general purpose register, and then all the bits in that instruction except those 24 bits are cleared. Okay, so that now R10, this register will contain only this 24-bit number, and from that number the execution will be actually transferred to the corresponding monitor routine, corresponding program. So you can understand how this is achieved here. This instruction is load LDR R10 comma this address. This instruction will load into R10 the content of the memory location pointed by this address. You can understand that this address is link register -4. Link register holds the address of the next instruction after the SWI instruction in the main program. Because that instruction occupies 4 locations, link that address -4 will give you the address of the actual SWI instruction. So this instruction, LDR instruction, will copy the instruction SWI into R10. It will copy the instruction SWI into R10. SWI is a 32-bit instruction. It is loaded into this 32-bit R10 register. Now the next instruction is bit clear instruction. It will clear all the bits except these 24 bits in that instruction. Okay, and therefore it clears the higher 8 bits which are opcode bits, keeping remaining 24 bits unchanged. Okay, and therefore R10 will now hold only the 24-bit number which is the part of that software interrupt instruction, and in the further part of this program that number is used to call the corresponding monitor routine to handle the required hardware module. So that's how this software interrupt handler works, and that uses this 24-bit number, immediate number in the SWI instruction, to decide which of the many monitor routines which are there in the operating system is to be executed. So that is the software interrupt instruction. Okay, next instruction is count leading zeros CLZ RD comma RM. Count leading zeros. This instruction is available only on the processors that support V5T architecture. That means only in the recent ARM architectures this instruction is available. It simply loads RD by number of leading zeros in RM. Sets RD to number of leading zeros in RM. That means it will just count the leading zeros in register RM. Starting from the MSB side, it will just count the zeros till the first non-zero bit is encountered, and that number of zeros will be loaded into RD. See, for example, if you give this instruction, suppose you are loading R0 by this number, 32-bit number, and then if you give this instruction, then it will count zeros, leading zeros in R0, and that number will be loaded in R1. So in this number which is there in R0, you can see that number 1, 2, 3, 4, 5, 5 into 4, so 20 zeros are there, and there are 3 zeros here additionally in this hexadecimal 1. There are 3 zeros, so 20 plus 3, so number of leading zeros is 23. So R1 will be loaded by 23 decimal or hexadecimal equivalent to 23. So that's how this instruction works. Next instruction is swap instruction. So this instruction is swap or swap byte RD comma RM comma square bracket RN. It can swap either a word, it may be signed or unsigned, or it can swap unsigned byte. There are 3 operands. Out of them, 2 are general purpose registers and 1 is the memory location. The operation of this instruction is shown here. It will first of all copy the content of this memory location pointed by this RN, into RD, and then it will copy the content of RM to that memory location. So that's how the numbers are exchanged between these two and the memory location. Content of the memory location is stored in RD and content of RM is again then copied into RN. Now in this case your RD and RM can be same registers. Okay, for example, if I give the instruction like this, swap R5 comma R5 comma say square bracket R4, then you can see that effectively the content of this memory location pointed by R4 and content of R5, and they will be swapped with each other. Okay, so that's a swap instruction. Now there are some instructions which are associated or which deal with the CPSR and SPSR registers. Now current program status register or saved program status register is a special, or these are the special registers in the ARM processor, and there are some instructions which are concerned with these registers. Actually, whenever any of the bits in CPSR or SPSR are to be modified, then they cannot be modified directly. The procedure required is that the content of CPSR or SPSR should be first of all copied into a general purpose register, then the bit should be modified, and then that pattern should be put back into the CPSR or SPSR. This instruction performs the first step of this out of these 3 steps. So this instruction allows to copy the content of CPSR or SPSR into a general purpose register. So the instruction is move status register to a register. Move status register to a register. It may be CPSR, current program status register, or it may be saved program status register. Content of any one of them will be copied to a general purpose register. So that's the operation. Okay, so here you get the content of these registers into a general purpose register. Then you can modify the content of these registers if you want. Then the next instruction does the last step, that means copying the content of these status registers, copying the content of the general purpose register back to the status registers. So the instruction is move register to status register. So it will copy the content of the register to one of these status registers. Either there are two forms of this instruction. Here it may be a register, general purpose register, or it may be a 32-bit immediate number. Okay, both possibilities are there. Okay, anyway, the content will be copied to the status registers. Here these instructions, you can see that here field is mentioned, and that field is one of these four. Actually, the 32-bit status register is divided into four fields of 8-bit each. From the least significant side, bit 7 to 0 is called as control field, because these bits, they contain control bits. Next bits 8 to 15 is called as an extension field. It is not currently used in the ARM processors. Next 8 bits 16 to 23 is called as status field. This is also not used currently in the current processors. And the last field is bit 24 to 31, uppermost 8 bits. It is called as flag field, because these bits, they mainly contain the flags. Okay, so that is how the status registers are divided into four fields. These instructions, they allow only one field to be modified at a time. So here you are supposed to mention one of these fields. So here this field may be either C or X or S or F, and this instruction will modify only that field. It doesn't allow all the bits of the given SPSR to be changed at once. Only the specified field can be modified. Okay, so that's how this instruction works. Of course, if you are using this form of that instruction, where you are giving the pattern in as a 32-bit immediate number, if the operand is a 32-bit immediate number, then only flag field can be selected. In that case, the field can be only the flag field. If you want to modify any of the remaining fields, then you have to follow use this particular the form of this instruction. So that's how this will allow you to modify one of the fields of either CPSR or SPSR. So these are the two instructions associated with CPSR and SPSR. Okay, you can just see an example. For example, suppose you want to set only carry flag without affecting other flags. Then what you are supposed to do is that you have to copy the content of that CPSR into a general purpose register, then modify the carry flag, and then put the content of that register back to the appropriate field of that CPSR. So this instruction will copy the CPSR into R0, 32-bit, all the 32 bits are copied in R0. Then this instruction will just set the required flag. It's a OR instruction. It ORs this pattern with the content of R0. So wherever you have bit 1, okay, this is 31, 30, 29th bit. D29 is the bit of CPSR, which is the carry bit, and therefore when you OR with R0 this pattern, then only that bit will set, carry bit will set, and that will be stored in R0, and then you can copy content of R0 back to the appropriate field, flag field of CPSR. Okay, so with help of these three instructions you can set the carry flag. So these are the instructions which are associated with the most important register CPSR and SPSR of this ARM processor. Okay, so that's how we have gone through the whole instruction set of the ARM processor. Before we end, just have a look at two important features of the ARM instructions, as we have noticed that all the ARM instructions are conditional instructions. Every ARM instruction has a condition field, and that will be executed in the program only when that condition is true. Okay, of course, if you put always as the condition, then that instruction will become non-conditional. But it is under the control of the programmer to make whether he can decide whether to make the instruction conditional or unconditional. Secondly, as far as data processing instructions are concerned, the data processing instructions will not affect the flags always. Again, the programmer can decide whether they should affect the flags or not, and therefore for that suffix s is provided. If the suffix s is added to the instruction, then only those data processing instructions will affect the flags. If s is missing, then that instruction will not affect the flags. The flags will remain unchanged. So unlike in any other microprocessors, these are some special features of the ARM processor, that all the instructions are conditional, and a programmer can decide whether any given data processing instruction should affect the flag or should not affect the flag. Okay, so that is all about the instruction set of the ARM processor. Thank you.